Yes, this is the video for beginning chapter 5 and then for section 5.1. Now, in this video, we'll talk about areas and distances, and our learning objectives are the following. We will try to estimate area under a curve using the recorded right endpoints, the left endpoints, and then the midpoints of 4 intervals. And then also estimate the distance traveled by particle or particles, okay, by particle using right endpoints, left endpoints, and then what, midpoints. Okay, now let's start with the area problem. Now, if you remember, and in trying to define derivatives and then limits, we started with the tangent problem and then the velocity problem. And so we use that to be the center part of what the differential calculus that we have been talking about from chapters 2, 3, and 4. Now, in the same manner, we are going to use area and distance problems to formulate the idea of what we call definite integrals, which is the basic idea of our integral calculus. So let us consider the area of a region S as given here. All right, S, this region. So that lies under the curve. And this function f of x is continuous and is from between the intervals a to b. Okay, so we're going to estimate, okay, to try to find the area under this curve. And it's not easy to find. So we develop what we call an intuitive word approach using what rectangles. Now, basically what we know that since we can find the area of a rectangle, which we know that is what length times the width, okay, area of a rectangle is length times the width, okay, we can partition this into what rectangles, all right, and some of them will be, say they have this rectangle that I can find the width, and then the width has the same, we're going to partition that into rectangle with the same width, and the height will be the f of x. So it depends on where the height is. So if you are talking of this height, then this would be the f that we are doing deal with. Okay, so that's the approach. So what are the steps that we take? Okay, the first step is that, so we are going to approximate this and then take the limits as the number of what rectangle increases. So we'll define that in a minute. But first, let's look at the steps. Okay, so we are given the interval a to b. We're going to partition this interval into sub-intervals, okay? And so we're going to denote x1 to x2, that's the first interval, x2 to x3, x3 to x4, xn minus 1 to xn, where we will say that your x1 here is equal to the lower limit of the endpoint on the interval, and the xn is what is your b. These intervals are the widths of the rectangles that we are talking about, okay? And they are the same. Don't forget they have equal subintervals, okay? Now we're going to let delta x be the width of each of the rectangles. Now if they're going to be equal, then depends on the number of rectangles, okay? There are n of them. So here we have for n rectangles, is the number of rectangles, and then the delta is the width, is given by what? The b minus a divided by the number of rectangles, which is this one right here. Okay, that's step 2. Now, after we have done that, then we can consider what? The left endpoints. So that means that if I consider this in the first interval here, I'll use x1. I'll use x1 for that, and then the left endpoints will be this, okay, or to the end. Now, if you are dealing with the right endpoints, then we'll be using this x2, x3, x4, x5, and then up to xn, okay? And then if you are using the mid endpoints, we're going to denote it by what? X star 1, which is take the first subinterval, x1, and then x2. So you find the sum and find the average, basically the middle, which is the x1 plus x2 divided by 2. And then for the second subinterval, that we denote by x star 2 is what? The sum of the interval endpoints divided by 2. So find the averages of them. Okay, so this is go all the way to the end. Now, let us consider an example and see how we'll find this. So I want to use this, this parabola. Okay, so use rectangles to estimate the area under the parabola y equal to s squared from what? 0 to what? 0 to 1. Okay, the parabolic region as illustrated in this diagram. Now, as you can see, this is a parabola. Now, from 0 to 1, this function, what is happening? The function is what? This is that's my y. Okay, and this is what? This y is what is increasing. Okay, it's increasing. And so we're going to partition this interval from 0 to 1. Okay, where we're going to say that x1 is your 0. We're going to use what? 4 rectangles. So it means that my n is equal to 4. So my x1 is 0, and then my x4 is going to be what? Is going to be 1. So how do we partition this? Okay, now don't forget that what is my delta x? My delta is what? B minus a divided by what? N. So in this case, my b is 1, my a is 0, and then my n is what? 4. This is what? 1/4. Okay, so if I partition this, the first subinterval will be from 0 to what? 1/4. Okay, the second subinterval will be 1/4. And if you add 1/4 to 1/4, you get what? 1/2. Okay, and then the next one will be from 1/2 to what? 3/4. All right, and then finally you have what? 3/4 to what? To 1. Okay, so here I have, this is 1/2. That is what? 3/4. And this is what? That is 1/4. Okay, so we're gonna have this and partition. This is my intervals. All right, this is the intervals where x1 is what? Is 1, 0, and the x4 is what? Is 1. Okay, so how many subintervals? 1, 2, 3, 4. Okay, so we're going to use the rectangles considering what? The left endpoints, the right endpoints, and then the midpoints. Okay, so let's consider them individually. So A, okay, so A, we are using what? Leftward endpoints. Okay, so don't forget we have these intervals, 0 to 1/4, 1/4 to 1/2, 1/2 to 3/4, and then we have what? 3/4 to what? To 1. Okay, now if I draw my diagram, okay, don't forget my n is what? It's 4. So we basically want to find L of 4. All right, so that's the notation. Now we know that our delta x is what? It's b minus 1, sorry, b minus a over what? N, which is 1 minus 0 over 4. That is give me what? 1/4. Okay, so let's draw the diagram here. Okay, the same function. Okay, and I'm going to start from, I'm going to draw it like this. Okay, so this is be my 1. So we have this. Okay, and this is what? This is 0, and that is 1. So this is half, this is 1/4, and this is 3/4. Now, if it says the left endpoints for this first interval from 0 to what? 1/4, okay, this subinterval we are using the left. So let me use the different color. Okay, so the left is what? Endpoint is 0, which is just going to be on that same line. Okay, so that's my rectangle. If I consider between 1/4, and then 1/2. The left endpoint is this, okay? And that gives me this what? This rectangle. Now consider 1 and 1/3, okay? The left endpoint is 1/2. So where it meets, and then we'll draw and then get this. So this is the what? That's the rectangle. And then the last but not least is between this and that, okay? So the rectangles, this is my y, the same, y is equal to what? X squared. Okay. So what's my L4? My L4 is given by where I have all this, okay. So my L4 is given by this formula. Okay. So L4 is equal to what? The sum, okay, I to what? I to 4 of the function f of xi times what? Times the delta. Okay. Now basically what this is saying is that this is the sum, means that it's going to be f1, okay, fx1 times delta x plus fx2 times delta x plus fx3 times what? Delta. So we are using the left endpoints, that is x1 here. This is x2, x2 to x3, x3 to so 1, 2, 3, 4. Okay. So x1, x2, x3, x4, and this is x4, x5, and then what? X4, and then what? X5. Okay. So we have this. Okay. So when you have this is a delta, then you're using the left endpoint, so the x1, x2, x3, and the x4. Then plus f times x4, and then what? X. All right. Now, what is x1? So the function is your f of x in this case is what? Is the x squared. Okay. So when you say f of x, x1 is basically what? F of what? 0 times delta, which is 1/4, plus f of what? 1/4 times 1/4 plus, okay, f of 1/2 times 1/4 plus f of what? What do you call 3/4 times what? 1/4. Okay, 1, 2, 3, 4. All right. Now, as you can see, this is the same as what? Finding f of 0 plus f of 1/4 plus f of 1/2 plus f of what? 3/4. And then you multiply, because you can, 1/4 is multiplying everything times what? 1/4. So this is what? 0 squared, because my f of x is that, the 1/4 squared plus 1/2 squared plus 3/4 squared, okay, 3/4 squared, then everything times what? 1/4. That gives me 0 plus 1/16 plus 1/4 plus 9/16, okay, everything times what? 1/4. Okay, if you evaluate this carefully, you are going to get 7/36. Okay, and that is approximately 0.21875. 0.21875. Okay, so that gives me the what? The left end point of this what? Estimate. Now, as you can see, this one, because look at the diagrams, look at the rectangles, you see that it underestimates it. If the function is increasing, this So we say that the L4 under what? Estimates the area. Okay, now let's go to this function. This is for when what? F is what? Increasing. All right, let's go to the second part using the right what endpoints. Okay, so here I'm going to write the same intervals, 0 to 1/4, 1/4 to 1/2, 1/2 to 3/4, and then we have what? 3/4 to 1. Okay, so here again, my n is what? N is 4. That's 4 rectangles. And then we're going to the right endpoints. Okay, let's have our diagram and see how this works. Okay, so here is our graph. Okay, and that is 1. So we have, it goes, that is 1. Now we have, this is my half. This is my 3/4. Here is 1/4. And that is what? That is 0. So if I'm using the right endpoints, okay, that is we 1/4, 1/2, 3/4, and then 1. So I use the rectangle and then I estimate that. So this gives me this angle, that rectangle. Then for the second subinterval, I use a right. So that goes and I get this. This gives me that rectangle. Then I use that. When it hits the graph, then you extend it and draw a rectangle. Okay. And then finally you have, this is 1. It goes and then that. So you have 4. So you can see that if it's a function is increasing, okay, it is the right endpoint will overestimate it. Okay, this is the function is still y equal to what? S squared. All right, so what is my R subscript 4? This is the sum from from 1 to what? 1 to 4. Okay, 1 to 4 of what? F of xi times delta x. Now, what is delta x again? It is what? 1 minus 0 over what? 4. That is 1/4. Okay, so we do it the same as we did before. So this is equal to f of what? F of x, x2, plus f of x3, plus f of x4, plus f of what? X5. Now don't forget that when I label my x's, okay, this is my x1, that is x2. Okay, this is x2, that is x3. This is x3, and then x4, and then what? X5. Okay, so when you have that, then we have this. We're gonna have all this, okay, because we're using the right endpoints times what? Delta x, because each of them multiply because the length of the area of a rectangle is what? Length times the width. Okay, so the width in this case is your delta x, and then the length will be the function value at say 1. Okay, for the last one. So that's why we are calculating like that. So therefore, this is what? F of what? F of 1/4 plus f function value at what? 1/2 plus the function value as what? 3/4 plus the function value at what? At 1. And then we multiply this by what? 1/4, because that's delta that's we calculated there. So this is what? F of x is f means s squared. So this is 1/4 all squared plus 1/2 all squared plus 3/4 all squared plus 1 squared and then we multiply this by 1/4. Okay, so this gives me 1/16 plus 1/4 plus 9/16 plus 1. Okay, times 1/4, and that will give me 15 over 30 what? 36. So 32. Okay, 15 divided by 30 what? 32. Okay, I think let me go and make this over here. This is not, I made a mistake. This is so 7 over 32. Okay, not 7 over 36. Okay, so then this is approximately 0.468775. Now, as we can see, when the function is, if f is increasing, okay, then the Rn what? Overestimates. Overestimates the area. Okay, so this is more than that. All right, so now let's check the midpoint. Okay, the midpoint of this this function. This how does the midpoint work? Okay, so let's go to part C. Part C is what? Using the what? The midpoint. All right, so again, let us write our intervals. It is 0, 1/4, and we have 1/4 and 1/2, and then we have 1/2 and 3/4, and then we have what? 3/4, and then 1. Okay, now again, my n is 4. My delta x is what? 1/4. So that doesn't change. Okay, so then let's see that the graph, how the graph will change here. Okay, I still have my graph going like that. It's increasing. This is my 1. That is 1/2. That is 3/4. This is 1/4. And that is what? 0. Now the rectangle should have what? Equal width. All right. So this is my, okay, that's 1. All right. So this is the function y equal to what? X squared. Okay, so he said the midpoint. Now the midpoint of this, okay, we're going to determine it by x star 1. That's the middle of this interval is x star 2. The middle of that is what? X star, and then 3, and then here is what? X star 4. Okay, so if I go the midpoint, when I stand that from that point, when it meets the graph, then I stand it to the right and then to the left. So I get my rectangle. Then I do the same. I stand it to the right and to the left. Then I get my second rectangle. Okay, and I stand this one. Then I stand it to the right, to the left, and then to the right. Then that gives me that. And then finally I have what? We extend that. I use broken line, dotted line. And that gives me this. So from the graph, you could see that the midpoint would definitely what? Would be a better estimate, because you see, you can have the same area overestimating and the under. So it's a better one. So this is still my F. Now, what is X star 1? X star 1 is what? X1 plus X2 divided by 2. So in this case, it's going to be 0 plus 1/4 divided by 2. Okay, and that gives me 1/8. Then what is x star? X star 2. It will be the second interval, add them, so that is 1/4 plus 1/2, all divided by 2. If you simplify, you get 3/8. And then you have x star 3 will be the third subinterval. It will be 1/2 plus 3/4, all divided by 2. And that gives me 5/8. And then we have the last one, x star 4 will be 3/4 plus 1, all divided by 2. And that gives me 7/8. Okay, so our M, because the midpoint is in the part M4, it's what? The sum, okay, from I equal to 1 to 4, and the f of S star I times delta what? Delta X. Okay, delta X doesn't change, right? So if we do this is equal to the f of what? The star X star 1 plus f of X star 2 plus f of X star 3 plus f of X star 4, everything times what? Times delta what? Delta X. Okay, so this means it's the f of X star 1 is what? 1/8 plus f of 3/8 plus f of 5/8 plus f of 7/8. Okay, everything, one is evaluated times what? Times delta X, which is what? 1/4. So this is equal to 1/8 squared, because the function is what? X squared, plus 3/8 all squared, plus 5/8 all squared, plus 7/8 all squared. Then everything times what? 1/4. Okay, 1/8 is 1/64 plus 9/64 plus 25/64 plus 49/64 times 1/4. Okay, so if you evaluate that and simplify, you get what? 21/64, which is approximately 0.328125. Okay, see? So with this function, y equal to the function y is equal to s squared is an increasing. We have seen that the lower limits, lower endpoints, L4 underestimates, the R4 overestimates, and this is more accurate. Okay, so we have the following remarks. Okay, the first ones that said that for an increasing continuous function, the left endpoints underestimates, the right endpoints overestimates the area. Okay, on the other hand, and for a decreasing continuous function, the left endpoint actually overestimates, and then right endpoint underestimates the area. Okay, second, if the sums, okay, that's like we did, the sums overestimates, it is called what? Upper sums. And if underestimates, it is called what? Lower sums. So among all the three estimates, the more the number of rectangles that we use. So if we increase the n to 5, 6, 7, or to 1,000, then the better the what? The estimate. And then when that happens, takes me to the fourth remark. The midpoint estimate is better than the others. However, as the number of rectangles n increases, all the three estimates are equal. This leads us toward the definition in the next word, the formal definition in the next slide. And what is it? It says that, therefore, we define the area of the region, okay, S in the following way. The area A of the region that lies under the graph of continuous function f is the limit. Remember, we use the differentiation, we use the limit. If you remember, we find it in chapter 2. The sum of the areas of approximating what? Rectangles. That is, your area is equal to what? The limit as n goes to infinity of the right endpoints, the left endpoints, and the midpoints, and they are all what? Equal. Okay, so in this case, for my interval where I have this interval x1, comma x2, and then x2, comma x3, and then goes so to what? xn minus 1, and then xn. Okay, you will notice that the right endpoints will pick what? Okay. Actually, I think the right endpoints will start from x2, x3. If this in this case, I'm starting with 0, okay? 0, 1, and then 1, 2, and then like that. So that's why it is x1. So this case, the right endpoint is x1, x2 in that order. See that? So that gives me that. The left endpoints will be what? x0, x1, x3, x4, and xn minus 1. So it ends there. And then the midpoints is the average of each one of them. Okay? So that actually brings us to that first part, using raw rectangles to estimate the area and the curve. Right? Then they go to the second part, which is the distance what problem. Okay, distance problem. So in a similar way, if I have, okay, if you consider distance problem, we want to find the distance traveled by an object during a certain time period. If the velocity of the object is known at all times, okay, of a time interval. If the velocity remains constant, then this distance problem is easy to solve. Okay, but on the other hand, if it is not constant, then it is not easy. Okay, so if I have a velocity and a time, then the distance is given by the formula velocity times what? Time. So just like the area, okay, where it is what? The length times the width. So we have the width and then the height. It gives you the function value at what? Which endpoint of the interval you are considering. All right, so now let's consider one example. Suppose that the odometer on your car is broken and you want to estimate the distance driven over 30 seconds time interval. Okay, so you take a speedometer readings every 5 seconds and record them in the following table. Okay, find the lower what and upper estimates for the distance traveled during the 30 seconds. So here is what you did. So that's 0. Your odometer is broken, so you read what? 17 miles per hour. Then 5 seconds later, 21 miles per hour, 10 seconds in that order. So 30 seconds, you had 28 miles per hour. Okay, now as you can see, this is the second, this is minutes and hours. So we want them to be in the same what? In the same units. Therefore, we know that 1 miles per hour is the same as what? 5,280 feet per, divided by 3,600 per feet per second. So we convert every one of this. In other words, we multiply this 17 times, this ratio here gives me 25. And then you do that and you get all these values that we have there. So for 0, you have what? 25, 31 in that order. Now, what do you see? What do you see about the velocity? Okay, for this time interval, you could see that it is what? It is increasing steadily. It is increasing steadily. So if it's increasing steadily, in terms of what? Ln, Rn, what can you say about them? If it's increasing, which one overestimates? Okay, the right endpoints overestimate. The lower endpoints will underestimate because it is what is increasing. All right, so then we're going to use this table, the second one, because they are in the quantities the quantities are in the same what units. All right. So then let us see how we do this. Okay. So to find the distance, okay, if I'm considering the interval, the first interval in this case would be what? From 0 to what? 0 to 5, that is 1. And then the second is what? 5 to what? 10. The third is from what? 10 to 15. And then we have what? 15 to 20. And then 20 to 25. And then we have what? 25 to what? 30. So how many subintervals? 1, 2, 3, 4, 5, 6. All right. So to find the distance for the first interval, it's going to be what? The 25 feet per second times time. And that will give me everything in terms of what? Feet. So that's 5 seconds. Because the time elapsed is what? It's 5 seconds. If I'm using the what? The left endpoints. If you're using the right endpoints, it's going to be 31 times 5. Okay? Because of the time interval. Because guess what? Your delta x, okay, your delta x in this case is going to be what? It's going to be 5. Okay, it's going to be 5. Okay, which is the same as what? 30 minus 0 divided by, because you have 6 subinterval over 6. That is why you have what? You have 5. Okay, subinterval every 5 seconds. All right, now, so what we do is that it says that during the first 5 seconds, let's calculate that, like we said. The first 5 seconds, if we are using the what? The beginning, the velocities at the beginning, which is the same as what? The left endpoints, then it's going to be what? 25 times 5 seconds, which is what? 125 feet. So what we are doing here is that it is this 25, because we are using the beginning of each time interval. Then that's going to be what? 25 times what? 5, because the delta x is what? Is 5. The second subinterval is going to be what? 31 times 5. Okay, 35 times 5, 43 times 5, 47 times 5, and then 45 times 5. Okay, because we are using the what? The left endpoints. So if you continue like this, we find the second, like I said, it will be 31 times 5 seconds, which is 155. So what we do is that we are using, don't forget, we are using the left at the beginning, the velocities at the beginning of each. Okay, so we have 25 times 5 plus 31 times 5, 35 times 5, 43 up toward 45 times what? Times 5. Okay, if you go back to the interval, see the 45, that's where we have the 45, it ends there. All right, so then when you evaluate that, you get what? 1,130 feet. That's the distance travel. Now this is what? Lower estimate for the distance what? Traveled, because it is increasing steadily. All right, the velocity is increasing what? Steadily over the time period, 30 seconds. Okay, now if you continue, this time we want to find the velocity, use the velocity at what? At the end. This is the right endpoints. Okay, so for the intervals we have there, okay, let's write them. The first one is the subinterval is 0 and 5. And the second is 5 to 10. Okay, 10 to 15. And then 15 to 20. And then 20 to 25. And then finally you have what? 25 to 30. So if you are using the velocities at the what? At the right endpoints, that is at the end, the right endpoint. So they will consider the velocities at what? At 5, the velocity at what? 10 seconds, 15 seconds, 20 seconds, 25 seconds, and then 30 seconds. And so for 5 seconds is what? The velocity is 31 times 5. And at 10 seconds is 35 in that order. So at 30 seconds, it was what? 41. Now when you do this is 1,210 feet. That's the distance travel. So again, As the function is, because the velocity is steadily increasing, it is what? It is the upper estimate. Okay, so that will do it for this section. We'll consider other examples in class on Friday. Thank you. Bye.